Okay, well, looks like the number has increased sufficiently. I'm sure people will still join, but welcome everybody. Thank you for joining. Today we are very happy to have Tessa Baker from the Institute of Cosmology and Gravitation, where she's a professor of cosmology. You know her for her research in cosmology and on modified gravity, from her contribution to Euclid, and more recently for her active role in the LBK collaboration, always with an eye on modified gravity and testing gravity, maybe I should say, rather than modified gravity. So Tessa, the floor is yours. We can take questions during the seminar. Raise your hand, please. I'll try to keep an eye on the hands, and I'll let Tessa know if there's a question.
All
Floor is yours.
right. Great. Let me just start a couple of timers my end so I can make sure I'm talking to you for an appropriate length of time. Okay. Hi, everyone. It's a real pleasure to get the chance to talk to so many people, spread across different institutes in one setting. As Alessandra mentioned, my name's Tessa. I'm a professor at the Institute of Cosmology and Gravitation at the University of Portsmouth in the UK. And if we can get this working, there we are. I do like to show people a picture of Portsmouth at the start of my talks because it's not a super famous town outside of the UK. So it's down on the south coast of England, and as you can see here, lovely seafront. Of course, it's always this sunny, not really. But my institute, the ICG, as it's known, is here. And we're situated just in this building here, about 10 minutes walk away from the seafront. So it's a really lovely environment to be in. Okie doke. But down to business. So my title today is quite general, right? I called this Progress in Gravitational Wave Cosmology. And it's really an excuse to tell you a bunch of things, but it will mainly be centered around presenting the latest cosmology results from the LIGO-Virgo-CAGRA collaboration, with a few other things tucked in. So this is our outline. This is what we're going to do. So first of all, we'll talk about the latest data release from the LIGO-Virgo-CAGRA detectors. We'll see a little bit what's in that. And then secondly, I'll explain the methods that we apply to this data in order to answer questions in cosmology. In the third section, I will apply these methods to this data and show you the results, which will be the latest gravitational wave constraints on measuring the Hubble constant and also some tests of modified gravity theories. And finally, time permitting, we'll wrap up by kind of putting this all in a broader context of gravitational wave cosmology, trying to scope out how things might evolve in future. And we'll also talk about a new kind of probe that's appeared recently. Okay, and so this is my lovely research group at the ICG, but as I've said, really a lot of my work today that I'm presenting will be really powered by 1,000 or so people in the LVK collaboration. Okay, so let's get started. What I am not going to do today is go through a sort of basic introduction of what gravitational waves are. I think probably after a decade, people have got a good sense of what gravitational waves are, propagating perturbations in the space-time metric. And you may also know that the major sources of gravitational waves that have been detected by the LVK collaboration, at least so far, are coming from binary black holes, binary neutron stars, and also the mixed case, so one neutron star and one black hole. Okay, and the numbers here just represent typical masses of these systems. And we make detections from these coalescences of compact objects with the aforementioned LIGO-Virgo-CAGRA detectors. So that means I have to show the obligatory aerial shots of the detectors. So the two LIGO detectors in the US, the Virgo detector in Italy. You can't show an aerial photo of CAGRA because it's underground. But I was very privileged to visit CAGRA a few years ago, and this is a photo I took in one of the tunnels. So I won't talk today about the detectors themselves. They're really incredible pieces of engineering, but that is somebody else's talk. So instead, I will jump straight into the latest data that has been released by the LVK collaboration. And this goes by the name of GWTC 4.0, that is Gravitational Wave Transient Catalogue number 4. And this is the data collected by the detectors from roughly May 2023 to January 2024. And so on this sort of little timeline figure here, you see the first 3 observing runs of the detectors. And then there's quite a large gap, which is certainly lengthened by the COVID-19 pandemic. And then we start O4 here. And actually, we have now completed the O4 run that finished a few weeks ago in November. But what I will be presenting is the first chunk of this O4 run, which we call O4A. And you can see here already that the Virgo detector was not online and contributing during this stage of the observing run due to some technical issues. And that is going to have a major effect on the results I will present you later today. So in this chunk of the first chunk of the O4 run, we have 128 new gravitational wave detections. So added to the 90 events that we knew about previously from the first 3 observing runs, that leads us to a total of 218 gravitational wave events in the public domain right now. And there's various ways of representing these gravitational wave events. I quite like this plot, sometimes gets called the Petri dish plot. So what you're seeing is the 4 observing runs glued together clockwise from sort of 12 o'clock here. So there's different sectors for each observing run. And all the dots here represent gravitational wave detections. The distance of the dots from the center represents their luminosity distance, their distance from us. The size of the dot represents its mass, and the intensity of the color of the dot represents its signal to noise in the detectors, or how loud it is. And this insert here is just a zoom in of the central region. So what this plot shows you quite nicely is just how dense the detections have really become in O3 and O4, or O4A, sorry, at least compared to the first 2 observing runs where we only had about 11 events in total. So many, many more events. You also see in O4A, we start to populate the outer ring of this Petri dish. There's no numbers on here in terms of distances, but you can see there are more distant events than in O3. And also within the O4A sector, we've got the largest and most massive event to date, and also some of the most high signal to noise events. So the longer we observe for, the more interesting stuff we find. So what's in this catalogue? Predominantly it's new binary black hole detections, but there are 2 systems that have neutron stars in them. And actually one of these was detected in the engineering week that happens a week before the official observing run starts. That seems to be a kind of history of that kind of thing happening. So one of these neutron star containing events is clearly a neutron star black hole. You can see it represented here. But the other system was a very interesting one because one of the objects is what we used to call a mass gap object, although we might have to change that terminology. So we used to think that there should be a gap between where the heaviest neutron stars end and where the lightest black holes begin, somewhere between about 3 and 5 solar masses. And yet we've been finding objects that live in that mass regime, and we're not totally sure what they are. So it's just a nice example of how the more detections we get, the more we're kind of forced to change our sort of previous pictures of how compact objects form. I've mentioned already we had the loudest signal to date that had a signal to noise ratio of about 42 in the detectors. And the mass range of black holes in this catalogue now spans from about 5.8 solar masses to a whopping 137 solar masses. So this is just a kind of quick teaser for the interesting things in the catalogue. There's many more papers from the collaboration detailing this catalogue and some of the special events which you can find here. But my role in the collaboration is as a cosmologist. And so now I'm going to turn to really focusing on how we extract cosmology from these detections. And so we're going to meet three different methods today, which we call siren methods. And ultimately, they are all probing the relationship between luminosity distance and redshift. So to illustrate this a bit further, I've got an expression on the slide here for the amplitude of a gravitational wave from a very simple system. So it's a binary black hole, non-spinning, perfectly circular orbit to lowest post-Newtonian order. So just the simplest thing I could write down. And what this depends upon is the redshifted chirp mass. So this curly M here is the chirp mass, which is a particular geometric combination of the masses in the binary. But it appears in this amplitude with a factor of 1 plus redshift folded in. Again, that's going to be important later. And then apart from a bunch of sort of angular factors to do with inclination and polarization, the other quantity of key importance to us today is the luminosity distance, okay, which is given by the standard formula here for an FRW cosmology. And of course, sitting in this relation, in this Hubble factor, are the most important numbers in cosmology. So the Hubble constant, the dark matter fraction, the dark energy equation of state, etc. So what gravitational waves give us is a measurement of the left-hand side of this equation. They tell us about luminosity distance. And if we can find a way to constrain the redshift variable here, we get access to these parameters. Okay, and that's what we're going to try and measure today. With the current data, predominantly the parameter we are most sensitive to is the Hubble constant. I won't talk really about the other two shown here. Okay, so we are getting into the method section now, where we're talking about these different techniques that go by the name of gravitational wave sirens. And what I'm going to do is sort of show you a slightly sort of sketchy, quick version of the Bayesian formalism that underpins these different siren methods. Oops, there we go. Okay, so what we are going to write down is the likelihood for one gravitational wave event. What's the likelihood for receiving a certain set of gravitational wave data, given a set of cosmological parameters I'll call lambda. So in lambda are things like the Hubble constant. When I come to do tests of gravity later on, we'll have some modified gravity parameters. They'll also sit in that vector lambda. And this object on the left, we can write as having been marginalized over another vector of parameters I will call theta. And theta is the set of parameters describing the compact object binary that merged. So the component masses, the spins of the objects, etc. So now we've got this, factor in here, which is P of theta given lambda. So it's quite a complicated object in general, but it holds things like the model for the mass distribution of compact objects in the universe. How likely am I to get a black hole of 30 solar masses, of 10 solar masses, etc., given the universe that I'm describing? There's a really important denominator here, which I won't talk about today. We sometimes call it selection effects, and it takes account of the fact that gravitational wave detectors are biased, by which I mean they don't sample the true population of gravitational wave sources uniformly. We are much more likely to detect massive events and nearby events because they cause a greater signal to noise in our detector. So that kind of bias factor is corrected for here. This object in the middle, the likelihood of this data given a set of values for lambda and theta, this is effectively the posterior samples that come out of gravitational wave parameter estimation pipelines. So there's a whole bunch of very clever people in the LVK collaboration who analyze the data coming off the detectors and work out what was this system that merged, that produced the waveform we received. What were its masses? And importantly for us today, what was its distance? And so that gives us PDFs effectively of those parameters. Now, there's just one more stage we have to do with this expression. So we can also write the item on the right as having been marginalized over redshift, which remember is something we cannot extract directly from the gravitational wave itself. And so now we've got this object in here, which is like a redshift prior. So where is the source likely to be in redshift space? Again, given a set of cosmological parameters. And the different siren methods I'm going to tell you about today correspond to effectively different ways to supply this redshift information. So the first way of doing this, the simplest way, is of course if we have an electromagnetic counterpart to our gravitational wave event. So we've got a wonderful multi-messenger event. In that case, of course, we find the host galaxy of the gravitational wave source, and we can measure a spectroscopic redshift for that host galaxy. And then this redshift prior is essentially a delta function, or close enough to a delta function. And that makes this expression really easy to evaluate. And this is what happened, of course, with our one and only bright siren. And in this case, the posterior you get on your cosmological parameters, which in this case we chose to present the Hubble constant, is shown here, overlaid on other measurements from the CMB and some of the low redshift distance ladder measurements. And so you can see it peaks in a very consistent place, but the width of this measurement is of order, eyeballing it, sort of 15 or so kilometers per second per megaparsec. So it's not enough to resolve the Hubble tension, but it shows you can measure the Hubble constant this way. And so we thought at the time, no problem, great first measurement. We'll just wait for more bright sirens to arrive, we'll combine the data, and away we go. We'll measure the Hubble constant, solve the Hubble tension, job done. And of course, that did not happen because we have not had any more bright sirens to date. So instead, we have to get a little bit smarter about how we supply redshift information about these sources. So this leads us on to method number 2, which goes by the name of spectral sirens. And this is something we can do when we have no electromagnetic counterpart. So we can do this with binary black holes, but we're not going to bring in any external information either. And you'll see why I say that in a moment. So just analyzing the gravitational wave data. And in this case, we can actually learn something about the redshift of the source from the redshifting of features in the mass distribution of compact objects. So remember, what we actually detect from our gravitational wave detections, what we measure, is the redshifted chirp mass. But what we would model when you run codes of stellar population synthesis would be the true chirp mass in the source frame of the object. And these two things are related by a factor of 1 plus redshift. Now, the true source frame mass is something that we try and figure out from the LVK data. And so this plot shows the latest mass distribution bounds from the O4A data. So what you've got on the x-axis is the mass of the primary, the heaviest object in the binary. On the y-axis is a rate in some units, not really too important today. And there are a couple of curves on here, but I ask you to focus on the orange one, which is sort of one of our headline models. And you can see this distribution of masses is not flat at all. It has features in it. In particular, there seem to be two clear peaks, somewhere about 10 and 35 solar masses. The regimes between and above these peaks are quite well described by power laws with some indices. So what's actually going to happen if we took the same set of sources and moved them to different redshifts? Of course, we would observe these peak features appearing at different masses because of this 1 plus z object here. And it's often helpful to think about this in terms of Hubble's law, just to get the scalings right. So if you, sorry, I'm just moving my little video screen around here. If you remember, we've measured the distances to these sources. If I increase the Hubble constant, I increase the redshift that I attach to that distance. So I push up this factor of 1 plus z, and that means that the masses here must be pushed downwards in order to keep this object on the left fixed. So what I find is that my inferred Hubble constant will go down and the peak will, sorry, if I turn up the Hubble constant, the position of this peak will shift to the left to get things in the right direction. So the presence of these features is actually informative. And what this means is when we do a cosmological analysis, on one hand, this is really useful, but on the flip side, we're going to have to infer these peak positions and all of the other parameters here alongside our cosmology. Okay, and so the name gets this name spectral sirens because this is just like the redshifting of emission and absorption lines with redshift. Now, I'm not going to show you results from this method alone. I'm going to tell you about the next method and then we will combine them. So the third method, which isn't really separate, but I find it useful to talk about separately, sometimes goes by the name of dark sirens. And this is something we do when we have no electromagnetic counterpart, but now we are going to bring in an external data set, which is a galaxy catalogue of galaxies observed in the region of the sky where our gravitational wave has come from. So if I bring back our likelihood expression that we had previously, in the case of the bright siren, we said this redshift prior was kind of just like a delta function at the redshift of the host galaxy. Well, what's going to happen now with our whole catalogue is that effectively this is a whole collection of delta functions, right? We don't know which galaxy is the true host, so we have to allow them to all be possible hosts. And this means from a galaxy catalogue in the right area of the sky, we can build a redshift prior that is going to be very, very featured. It's going to have lumps and bumps corresponding to where the galaxies are in redshift space. And what this integral is going to do is effectively overlap this lumpy, bumpy distribution with the distribution of the luminosity distance of our source, which was often a much smoother thing. And so it's kind of calculating a kind of like a convolution integral, if you like, between these two objects and finding the set of parameters, the Hubble constant that gives maximum support to these mutual distributions. Okay. Now, I've sort of introduced this as a separate method, but there's a bit of an abuse of terminology going on here. When I say dark sirens, what we really mean is doing this galaxy catalogue information plus the spectral sirens method that I talked about previously with the mass distribution. You can't actually separate them out. You can do the spectral sirens on their own, but you can't do the galaxy catalogue on its own. So we're going to combine these two methods. Okay, and what I'm going to do is I'm going to show you the results of those methods with the GWTC4 data that I introduced to start with. I'll just pause here for a second if there are any questions and also so I can grab a drink.
I don't see any hands raised, but please, if you have a question. No, I think you can continue.
Okay. If not, we can charge straight on to the results, which of course is the best bit. So I'm going to present the results from this paper that has the title of GWTC4, Constraints on the Cosmic Expansion Rate and Modified Gravitational Wave Propagation. This is a very long way of saying it's the latest cosmology paper from the LVK collaboration. I had the great privilege of being the paper manager for this paper, which means I organized all the Zoom calls to get together with the editorial chair, which was Danny Legee, organized Zoom calls, sent 1,000,001 emails, herded a lot of cats, and generally had the privilege to work with a lot of very talented young people working on this data. Okay, so there's a couple of bits of more specific setup I need to explain to show you these results. So first of all, we've talked about the mass distribution for compact objects that was important for the spectral sirens method. In this work, we are going to try using 3 different forms for this mass distribution. So the simplest one is quite similar to what I showed you before already. We call it power law plus peak. There's one peak feature here. And the second model is just a generalization of that, where we've got 2 peaks with locations mu g low and mu g high. Okay, and these distributions have been motivated by the previous LVK data sets. So these are good fits to the data up to the end of O3, and so they're sensible things to try with the O4A data. Now, these distributions describe black hole masses only, but a new thing that was introduced in O4A is that for the first time, we also have a parameterized mass distribution that describes the whole spectrum of masses, including neutron stars up to black holes. And you can see it's a lot more complicated. It has this complicated dip feature here, which is kind of replacing that mass gap I described earlier. So rather than there being no compact objects there, we're sort of allowing there just to be a possible suppression of objects in that range. So we'll use all 3 of those. We also have to use a parameterized form for the merger rate of compact objects. So we assume a form and then we fit its parameters. And for this work, we use something inspired by a McDowell-Dickinson parameterization. So that's intrinsically sort of associating that the rate of compact objects might follow a similar structure to the star formation rate in the universe. And this is quite a complicated parameterized form. It's got these 3 parameters, gamma, ZP, and kappa, which we would need to fit from our data. However, luckily at low redshifts, below redshift 1, where most of the LVK data is concentrated, this actually reduces more or less to approximately a power law in 1 plus Z with this power law index gamma. And I'm going to stress gamma for your attention because that's going to come back and haunt us when we see the results on modified gravity. Okay, the final bit of setup I need to do is to briefly introduce the galaxy catalogue that was used to do our dark sirens analysis. So we use a catalogue called GLADE Plus, which is described in these references here. It contains about 22 million galaxies in total. And GLADE Plus is not a new survey, it's an assembly, if you like, of 6 smaller surveys, correctly matching together the filters and the different bands from those surveys. And the reason you want to do that is because between them, those 6 surveys cover the full sky. And that's really important for gravitational wave cosmology because, of course, our gravitational wave events can come from any direction. The downside of this catalogue is that it is relatively incomplete. So the completeness in the K band of the catalogue, which is just the particular magnitude band we use, because it's color band we use, because it's the most well characterized. The completeness in the K band is less than 10% at redshift 0.2. So that means we're only seeing 10% or less than 10% of what we estimate are the true galaxies out there. And this is unfortunate because most of our gravitational wave data is further away in redshift than that range. So we haven't got great coverage of the full localization volume of most of our gravitational wave events. Okay, at least with this catalogue right now. On the image here, you see in yellow and blue in the background, that's the density of galaxies, the magnitude threshold of galaxies in the GLADE Plus catalogue. And the coloured blobs are showing you the 10 best localised events in the O4A dataset. And if you're used to looking at gravitational wave localization areas, you should notice that these are quite poor, right? They are all bananas on the sky. And that is due to the lack of the presence of Virgo in the O4A run. So if you have three detectors working at the same distances and triangulating, you can pin down your events to a relatively small region, something that might be an ellipse. But if you just have two events, so two of these colored circles, you get these bananas. And again, that is going to impact the final cosmology results. Okay, so let us look at the headline constraints. So here is our, what we call the money plot, right? It's our posterior on the Hubble constant. And this has been marginalized over 19 parameters describing our fiducial mass model, which is that full pop model that describes neutron stars and black holes, and the merger rate parameterization, the Maddow-Dickinson one. And what you're seeing in yellow is the bright siren result, the 1708-17 measurement. In red, we have the spectral siren measurement, so just using the mass distribution. And then in blue, we add to the red measurement the galaxy catalog component. Okay, so that improves the red a little bit, not a huge amount because the galaxy catalog is relatively limited, as I've described. And then in black, we've got the sum of yellow and blue, so bright plus dark sirens. And numerically, our central value is about 76.6 kilometers per second per megaparsec, plus 13, minus 9.5. Okay. So we're still not resolving the Hubble tension, but things are starting to improve. You see that adding the spectral and the dark sirens methods does add constraining power over the bright siren. Not a huge amount yet because of all the limitations that I've said happened in O4A, but those are things that will improve in future. Now, you might ask, what impact does the assumed mass model have on this result? So we've got the curves here for those other two mass models, the power law plus peak and the multi-peak model. You can see that they're slightly different. Multi-peak's just a little bit worse, but consistent shape. The power law plus peak really smears out the Hubble constant to high values. And this is because that particular model is actually now disfavored by the data. We know that you can't fit all of the structure in the mass distribution with just a single peak. So although it looks worse, we know this is not the right model to be using. We also play around with weighting the galaxies in the catalogue. So either saying that all galaxies are equally likely to be hosts, that would be the dashed line, or saying maybe very luminous galaxies have more stars, therefore more likely to have compact binary systems, and maybe more likely to be the host sites of gravitational wave events. However, at the moment, again, because of the limited extent of the GLADE Plus catalogue, it doesn't make a huge impact on our results. So those are the headline H0 constraints. What I also want to tell you about is the constraints on modified gravity, which was something new that appeared in this paper for the first time. It's what happens if you put me in charge of an LVK cosmology paper, is that modified gravity will find its way in. And what we did was we tested two forms for changes to gravitational wave propagation. So I've got on the slide here an equation describing the propagation of a gravitational wave, that's Hij, just across an FRW metric. And what you're seeing in the two coloured terms are two changes to this equation that happen in families of scalar tensor modified gravity theories. So these are sort of major kind of mainstream ideas about cosmological modified gravity theories. Experts in the audience might recognize these parameters as being the Horndeski parameters. That's just a name given to this family of mainstream models. We don't really need to know anything about that modeling today. So this term here is changing the friction. Whereas this term here is changing the propagation speed of the gravitational waves because it multiplies the factor of c that would otherwise be the propagation speed. Now, the propagation speed of gravitational waves was very well measured in the binary neutron star event 170817. So we're actually going to set that term alpha t to 0 today. And we'll focus our efforts on constraining instead the effects of this friction term. And what's going to happen when this term is non-zero, right? It would be 0 in general relativity. But what it will do is it will change the amplitude of your gravitational waves and how that amplitude drops off as your waves propagate. So in general relativity, that amplitude drops off as 1 over the luminosity distance traveled. However, if you solve this equation with this new term, alpha m in here, and I'm indicating that it's a function of redshift, what happens is that that distance that sits in the denominator of the amplitude is changed. And it now becomes an effective distance, which we will call the gravitational wave luminosity distance. Right? It's not that the gravitational wave is actually moved anywhere in distance space, it's still in the same place, but this number you interpret as a distance has changed. And so we often think about this ratio of these two distances, the gravitational wave one and the standard one, which would be the one you would associate to a supernova. And in general relativity, these two things would be the same. And the claim is that in a large class of modified gravity theories, this ratio would no longer be equal to 1. So what we go and do with our dark sirens method is we constrain forms for this ratio. And in particular, in the paper, we constrain 2 forms. One of them is taken directly from this computation of these effects in Horndeski gravity, so scalar tensor gravity. And in that case, this distance ratio, you can compute the solution of this equation, and it has this form here. So it's a little bit strange, exponentials and integrals and things, but the key thing here is that this alpha m object appears here. And to constrain this with the current data, we find it very difficult to constrain a function of redshift. So we make a very common modeling choice in the literature, which is to adopt an ansatz, or a parameterized form for alpha m, which is shown here. And in this case, we're kind of imprinting on the analysis our belief that cosmological modified gravity, we want to affect the late time universe. We don't really want to affect the early time universe. So this omega lambda, the energy density and the cosmological constant, just ensures that happens. It's something that goes to 0 at early times. And so then what we constrain is this constant of proportionality here, which we call Cm. The other form we're going to use is a little bit more of a sort of model independent form. It's a parameterized form controlled by this parameter xi0. General relativity is recovered in the limit of xi0 being equal to 1. And the claim made in this paper is that this describes a kind of very broad swathe, if you like, of the modified gravity model space. So we constrain both of these formats, and here are the results. This is just extending everything I told you previously about the dark sirens method. So on the left, we've got the Horndeski form. On the right, we've got that model independent form. And in blue and orange, they just correspond to different priors on the Hubble constant, whether we take a wide prior or a narrow prior. Ultimately, it doesn't make a huge difference. And so these are big analyses, but I'm just showing you the 2 parameters that are sort of the most correlated. So on the x-axis, you've got the modified gravity parameters. That's Cm for Horndeski, or xi0 for the model independent version. And the dashed line indicates gr. And on the y-axis, you've got gamma, which, if you recall, was the power law index of the merger rate. And so what we actually find is that modified gravity effects are correlated with this astrophysical parameter gamma, because what both of these things are doing is they are controlling how the number of gravitational wave events rises as you kind of move away from the Milky Way, right? As you look out in the universe, how steeply does that number go up? And that can be affected by changing the apparent distances of where all the sources are, bringing them closer or pushing them further away. or it can be affected by just changing the true intrinsic astrophysical rate of mergers. Hence, there is this degeneracy. We can't break it with the current data. The hope is that ultimately, with more events from the astrophysical side, we should get a better constraint on gamma, which you see is quite poorly constrained right now. But in terms of headline results, Cm is measured to about 0.3 plus or minus about 1. This parameter xi0 is measured to 1.2 plus or minus about 0.4. And so both of these results are consistent with general relativity. Okay, so that completes my sort of headline presentation of the latest LVK cosmology results. Obviously, there is a lot more detail in the paper, so I do encourage you to go and look into that. What I wanted to do in my last 10 minutes or so, 10, 12 minutes, would be to kind of set this in a context of where is this field going. But again, I'll take a brief pause here in case any further questions have popped up.
I don't see any hand raised.
Okay.
So I think you can continue.
Glad to hear everything is just crystal clear. Okay, so one thing we did in the LVK cosmology paper is we made what we think of as kind of like the timeline plot. And this reflects what has been the change in gravitational wave measurements of the Hubble constant by LVK collaboration. So obviously there might be external measurements as well, but these are our measurements. And timeline is going down from the top here. So starting with the bright siren, and then this first blue line here reflects an analysis of the first 2 observing runs with only 7 events in it. And then the next block is the analysis of up to the end of 03. So it's got about 45 events in it. And here we've got 2 lines because the orange is just the spectral siren measurement with the bright siren, and the blue is a dark siren's measurement with the bright siren. And then there's a reanalysis of 03 that happens a bit later on. And then down the bottom here, we have the current work where we've got 142 events going in. And what you might notice in this plot is that the first 3 sets of measurements, right, the error bars on H0 are just decreasing as you would expect. But then something slightly unusual happens where the error bars seem to get bigger again, even though we've added more events. So what is going on there? What is really going on is that these early analyses were overly constrained. So earlier on in 02 and 03, we were not able to do the full parameter analysis where we vary both the cosmological parameters and all the parameters describing the mass distribution. And that's what's being indicated by these dashed lines, is that these results have fixed mass distributions, which imposes a kind of overly informative prior on the Hubble constant. So it's not that things have got worse, it's that things were never quite this good as they were reported to be. And then what happened kind of in the gap between 03 and 04 is that we solved that computational challenge, and now we are able to robustly constrain the cosmology, the astrophysical, and the modified gravity parameters simultaneously. Now, 04A was the first time this was put into practice. So even though the improvement is not huge, and that's because of the shallow galaxy catalogue and the poor event localization, I put here, stay tuned for 04B. So the Virgo detector was back online for 04B. So certainly the localization of gravitational wave events is much better. And there will be results coming out which move the dial on constraining the Hubble constant. Now, you might ask, where is this going in future? Right, so the galaxy catalogue is currently a major limiting factor. However, of course, we have major stage 4 surveys happening, providing very large, very deep galaxy catalogues. And so the hope is one day to be able to use things like the DESI survey and results from the Euclid survey to actually serve as the galaxy catalogues for dark sirens. And in this case, we'll probably see a switchover where that becomes the dominant constraint. And there's a really nice forecast plot for this kind of work from Nicola Borgi and collaborators down here. So at the top here, they've got a forecast for the error on the Hubble constant just using the spectral sirens method, so no galaxy catalogue. And then in the bottom two panels, they bring in a photometric stage 4 and ultimately a spectroscopic stage 4-like survey. And you can see in the spectroscopic case, with 04 and 05 data, we get down to about 8% and maybe even 2% constraints on the Hubble constant. So all of this is to paint a picture that it's still relatively early days for the dark siren method. We've sort of ironed out quite a lot of the bugs. And what I think will be happening now, or I certainly hope will be happening, is a rapid acceleration now that we can use really capitalize on the much higher rates of data that are coming in, both on the gravitational wave and on the electromagnetic side. Okay, the last thing I wanted to tell you about, which is a little bit kind of snuck in here, but it's something I'm really excited about. So in my last sort of 5 or 6 minutes, I wanted to talk about a new method, which has really got a lot of attention and interest on arXiv over the past few years. So it's a new kind of gravitational wave siren, if you like, which is gravitational wave galaxy cross-correlation. So the fact that gravitational wave sources live in galaxies means that if you had a map of galaxies and a map of gravitational wave sources and you overlaid them, they should be correlated. Okay. So to present this briefly, I've got a slide that I've very gratefully stolen from Isabella Matos, who's a postdoctoral researcher in my group. She wrote it out so nicely, it didn't make sense to change this. But we compute a cross-correlation signal between these two traces. So we've got our map of galaxies, which is in redshift space, and we've got our map of compact objects or gravitational wave sources. So B here is for black hole, which live natively in luminosity distance space, as we've seen earlier. And you compute this thing here, and after a bit of algebra, it transforms into an angular power spectrum, which is this object CL down here. Okay, and the other factors here are effectively just bits of geometry that come out the computation. So this angular power spectrum of the cross-correlation between galaxies and gravitational waves depends on 3 quantities, right? The multiple number L, the redshift of the galaxies, and the luminosity distance of the gravitational wave sources, which here have been cut up into bins. And so you can make theoretical studies of what this cross-correlation angular power spectrum would look like. And this is a very nice piece of simulation work from João Ferri and collaborators down here for a 3G-like scenario. So Einstein telescope or cosmic explorer, where you've got thousands of gravitational wave events. Okay, and what you see in this space of distance and redshift is this bright track, which represents the peak of this cross-correlation signal. And the shape of this track depends on cosmological parameters that relate the luminosity distance and redshift. So these are really nice theoretical studies. There's been lots of other work done in the literature. And together with Isabella, João, our collaborators at Sao Paulo and Rio de Janeiro, and my group, we started asking, could we detect this in the current data? And so we applied our version of this method, which goes by the name of peak sirens, because we're looking for this peak in this cross-correlation signal. So we've been applying this to the current data. This is work that's due to come out very soon, hopefully in a week or 2. It's not quite out yet, so this is a little bit of a preview. So what we do is we take the gravitational wave events, or specifically 2 events, from the GWTC3 catalogue. So that's the one before O4A, because O4A wasn't public when we started this work. And we take the Glade plus Galaxy catalogue that we've met already today. And we compute this angular cross-correlation power spectrum. Okay, so this is the same plot as you saw before. It's the same object here, just much zoomed in to a very low redshift corner of this plot, where there are these two gravitational wave events that are well covered by the galaxy catalogue. One of them is 1908-14. One of them is 1708-17, which is the multi-messenger event. However, here we are using it without its redshift information. So we're pretending we never saw the EM counterpart, effectively. And so this is like a very low resolution version of the thing on the right. When you don't have thousands of events, you don't get this nice smooth curve, you get something kind of discrete. But we do see these bright peaks. And so we asked, is this a detection? How could you quantify whether this is you're actually detecting this cross-correlation signal? And so to do that, we had to make simulations of events like the two gravitational wave events that we're talking about, and simulate thousands of universes like the GLAY plus Galaxy catalogue. So we make about 6,000 simulations in total that reproduce these data sets. And the reason we do that is it enables us to compute covariance matrices, so we can evaluate a likelihood of how likely are these peaks produced by a true cross-correlation between gravitational waves and galaxies, and not just some kind of random alignment of galaxies. Okay, and so evaluating that likelihood, using both these events here, the significance of this detection is about 5.9 sigma. Okay, so we count that as a detection of this signal. And there's a lot of detail in the paper about these simulations, and also about how you kind of quantify this detection, which I won't go into today. But one of the cool things about it is you can then measure the Hubble constant from this signal. So remember, we said that the Hubble constant is kind of corresponding to the shape here. So this magenta line would be the Planck value. But actually from our data, we can do an inference of both the Hubble constant and also a parameter called gravitational wave bias. So gravitational wave bias is defined very analogously to classic galaxy bias, and it tells you about how the gravitational wave sources, the fluctuation in number counts of those, it traces the underlying dark matter field. And so our angular cross-correlation power spectrum basically turns out to be proportional to the dark matter power spectrum, with a factor of galaxy bias, which we estimate from the galaxy auto spectrum. And that allows us to constrain this gravitational wave bias factor, which has not been constrained before. And so doing this analysis with both these events, what you find is a measurement of the Hubble constant at about 67 plus or minus about 18 kilometers per second per megaparsec. You can see that here in blue. And that's about the same as the measurement you get out of the dark sirens work I showed you previously, just with a very small number of events. So this is a really powerful constraint on the Hubble constant. For the gravitational wave bias, we can't measure it precisely right now with two events, but we can place an upper bound on it. And so at about 95% confidence, it's less than about 4.3. And if you look at how this method scales with the number of events, we forecast that if you had 100 events like this, so 100 events like 1908-14, which is a well-localized event, you constrain the Hubble constant to about 4% or so. So this is just a little preview of some work that's coming out, and it's really exciting to see that this kind of landscape of gravitational wave cosmology is growing, and people are coming up with new methods, new ways this data can be used to do cosmology. All right, I have reached, I think, the end of my time today, so let me just wrap up briefly. So dark sirens are the current workhorse of gravitational wave cosmology. They're what the LVK collaboration uses to measure the Hubble constant. And I showed you that with the latest data, our measurement of the Hubble constant is this here. We also did tests for cosmological scale departures from general relativity. At the moment, our data is all consistent with general relativity. There are many moving parts in this kind of landscape of dark sirens work. So some things that people are working on improving right now would be allowing the compact object mass distribution to evolve with redshift. We think it probably does. That's no evidence for that in the current data, but as the data gets better, we think we need to include that. We also need to improve how we model the galaxies that are not in our galaxy catalogue that could be hosts of the gravitational wave event. Right now, we do very simple things, but we'd like to do something more physical. And finally, I just kind of snuck in at the end there that the cross-correlation signal between galaxies and gravitational waves is really exciting and is getting a lot of attention in the literature. And we've applied to the current data a version of that method called peak sirens, which does find a detection of the signal. And with that, I will happily wrap up and thank you for listening. And I hope there are some questions.
Thank you very much, Tessa. Please, we will be happy to take some questions. So just either raise your, maybe best raise your hand. Yeah, I see Francesca, please just unmute yourself and ask the question.
Hi, thank you very much for this very nice talk. I'm not in the topic, so I was able to understand, most of the things. So it means you did a very great job. So I was brought in by the possibility of solving that you could solve the Hubble tension. And I can see that there is potential for that because at some point you showed that plot with different measurements of H naught with all the large error bars. And so my question for you is, will you be able to make those error bars smaller and when? And then if you do, maybe, for example, your final measurement is going to fall on yet another different point with respect to Planck and all the others. And so at that point, that would not solve the Hubble tension, but add more mess to a messy situation. So yeah.
Okay, yes. So I think perhaps if I can get back to the most relevant plot, which is probably that one. Okay, let's take this apart. So first of all, when will we be able to solve the Hubble tension if we can? Well, of course, there's no guarantees of that. I think the galaxy catalogues will be a game changer. What we probably need, though, is access to full survey results from things like DESI and Euclid, right? Both those collaborations are starting to release data, but they release it in chunks, right? And it's maybe not the full sky. So to really get these kinds of results, we probably need those surveys to be finished and for the data to be public or shared between collaborations. So I don't want to speak for those surveys, but that's probably setting the time scale there. At the same time, there will certainly be systematics that have to be modeled both in the galaxy survey side of things and the gravitational wave event side of things. However, probably what this result will do is we'll just end up using the best gravitational wave events rather than all of them. So that might allow us to at least clear out some of the mess on the gravitational wave side. We'll just use the loudest, cleanest events that don't have evidence for precession and things like that could muddy the waters. If we found something different to the EM measurements, to both of them, I think that would be the coolest result ever, because then maybe there's something you can fit, right? Two results is a tension and you're not sure if somebody's got a systematic, but three results maybe is a trend. And then, there would be an interesting question for theorists. Can you find a theory that fits both the EM measurements, but also explains why gravitational waves see something different? So that could actually be a really useful signature.
Okay, I see. Great. Thank you.
Thank you.
Thanks.
Any more questions? Tessa, maybe while people are thinking, I can ask on your probably very last results slides on this peak sirens. So you mentioned that with 100 events like GW 190814, you will get to that few percent level of strain on H naught. But the key seems to be that they have to be well localized. So when is this something that you foresee with the LVK? Do we need to wait for next generation to get order 100 sufficiently well localized events?
Yeah, it's a good question. And I should say, you know, this scaling is very rough and ready. This is not from an accurate simulation. This is just from knowing that our constraint on the Hubble constant here goes as roughly as square root of the number of gravitational wave events in the limit where galaxy catalogs are good and deep, and it's the gravitational wave events that are kind of the limiting factor. When will we have 100 events like that? I think it's probably unlikely that O5, LVK05 will give you 100 events like this. I think we could get, a few tens of events like this, but maybe not that many. So then this number might fall in a slightly unfortunate gap between O5 and 3G, right? If there's nothing in that gap, then you've got to wait for 3G. But I think the hope is that with a full distribution of events in O5, we might get something close to this. It's very hard to say, but yeah, I think late O5 is a 75% of the way there.
Okay, fair enough. Thank you. Okay, I don't see any further hand raised. Oh, yes, Marlene, sorry. I'm losing the vision from close to the screen. But yeah, please.
Yeah, so I had a question about this Maddow-Dickinson parameterization. Because I've seen in some other works that people use a time delay distribution to relate the star formation rate to the black hole merger rate.
Yeah.
Which increases the complexity. I guess it also introduces more parameters. So my question is, did you consider this and rule it out because it doesn't improve the constraining power? Or?
So it's not considered in the LVK paper, but the reason for that being is we believe that we're just that could still be encapsulated by this Maddow-Dickinson form just with different parameters. So it's slightly confusing because when we say Maddow-Dickinson, people think of something that peaks at redshift 2, like kind of fits to star formation do. And our functional form doesn't have to do that, right? It can peak in a different place, it can have different slopes, etc., which could be the result of an intrinsic merger rate then convoluted with a time delay distribution. So we just try and fit the end product of those two stages, if that makes sense. And the claim is that we think that could still be well captured by the parameterization we've got, particularly because we're mainly only constraining the low end of that Maddow-Dickinson shape right now.
But sort of, what's the intuition behind that? If the merger rate distribution has the same shape as the star formation rate distribution, what does that say about the expected time delay distribution?
Well, if they were exactly the same shape, literally the constrained parameters came out very similar to the star formation rate, that would tell you that your time delay distribution would be almost flat, right? Yeah. If your time delay distribution had a very weird shape, then I think that could cause a problem and maybe would not be well fitted by our current parameterization. But I think it's assuming that it's fairly smooth and broad that would just map into shifts in the parameters of the form that we've got.
Okay, yeah, thank you.
Very good. So I think we can call it a day. Thank you very much again, Tessa.
Thank you very much.
See everybody at the next seminar colloquium.
All right, thanks.
Bye.